Similarly, work done in a polytropic process is also same as the work done in adiabatic process, which is P2 V2 minus P1 V1 by n minus 1, with the gamma having replaced by the value of n. The heat supplied during an adiabatic process was 0, but in a polytropic process we cannot assume that way. Therefore, we have to derive an expression for the heat supplied. Therefore, the heat supplied, we have the standard equation as work done plus change in internal energy, and the work done in a polytropic process is P1 V1 minus P2 V2 by n minus 1 plus the change in internal energy is standard formula of mCV into T2 minus T1. Now we convert all this into temperatures. We have the standard gas equation as P1 equals mR T1 and P2 B2 equals mR T2. So we replace these two terms with mR T1 minus mR T2 by n minus 1 plus mCV into T2 minus T1. So here we have mR T1 minus mR T2 by n minus 1 plus mCV T2 minus T1. So what we can do is we will take mR common, leaving us T1 minus T2 inside by n minus 1 plus mCV into T2 minus T1. So we realize that we convert this into mR into T1 minus T2 by n minus 1. We change the sign inside. We get mCV into T1 minus T2. So now we have m T1 minus T2 as common. We take out common. M T1 minus T2. If we take out common, we are left with R by n minus 1 minus C. So we have here m into T1 minus T2 and R by n minus 1 minus CV. So we need to eliminate this CV and convert into R, for which we have to do a small derivation of Cp minus Cv equals R, and we also know that Cp by Cv equals gamma. So we need to eliminate Cv. So let us get the value of Cv. So we will eliminate. So from here we get Cp equals gamma into Cv. So we'll remove this Cp and we'll replace with gamma into Cv minus Cv equals R. So Cv, if we take common, we get gamma minus 1 equals R. Therefore Cv equals R by gamma minus 1. If you know this formula, directly you can substitute. Otherwise you derive this formula to get the value of Cv as equal to R by gamma minus 1. So we'll substitute that value of Cv here to get m into T1 minus T2 R by n minus 1 minus, in place of Cv we will put R by gamma minus 1. Since R is common, we take it out. We are left with mR. We get here mR to T1 minus T2, and inside we get 1 by n minus 1 minus 1 by gamma minus 1. If we simplify this further, we get mR into T1 minus T2. We take LCM of n minus 1 into gamma minus 1. We get gamma minus 1 here minus n plus 1 there. So 1 gets cancelled. We are left with mR into T1 minus T2 by n minus 1. We take it out. inside we have gamma minus n by gamma minus 1. This is the formula for work done in a polytropic process. Now to summarize the formulas which we have in polytropic process. The expansion or compression follows the law PV by n is equal to C, where the values of n can assume from 1 to infinity, and then we have the work done equal to P1 V1 minus P2 V2 by n minus 1, and we have the heat supplied as equal to gamma minus n by gamma minus 1 by 2 mR into T1 minus T2 by n minus 1, and the change in internal energy remained as mCv T2 minus T1, which is standard for all the thermodynamic processes. Now we will take up some problems on this thermodynamic process. Let us take a problem on a constant volume process. The problem says a certain gas occupies a space of 0.3 meter cube at a pressure of 2 bar and temperature of 77 degrees centigrade. It is heated at constant volume. So this is what is important. You need to understand the process under which it is expanding or getting compressed at constant volume until the pressure is 7 bar. Determine the temperature at the end of the process, the mass of the gas, the change in heat energy, and the change in enthalpy. They are the constant volume that are given. So basically, in order to do the problems in thermodynamics, the first and the foremost thing that you need to do is draw a PV diagram and plot all the values that are given in the problem so that it is easier for you to understand. Let us now draw a PV diagram for this problem. Now he says certain gas occupies a space of 0.3 meter cube at a pressure of 2 bar and temperature of 77 degrees centigrade. It is heated at a constant volume process. Since we have pressure on the y-axis and the volume on the x-axis, and since we have a constant volume process, our graph goes from here to here, 0.1, 0.2. Now since it is getting heated and the pressure is rising, therefore the curve has a direction going upward like this, which indicates that the volume at 0.1, the initial volume is 0.3 meter cube and the initial pressure is 2 bar and initial temperature is 77 degrees centigrade. Heated at constant volume process until the pressure is 7 bar. Therefore here you get pressure as 7 bar. The volume remains same since it is constant volume process, and the temperature we don't know. So he's asking us what the temperature at the end of the process. So what is T2? So this is very important for you to draw the PV diagram for the problems on thermodynamic process so that you can understand it clearly. Now having drawn the figure, now let us write down the given data. Also, another important point you need to note is while writing down the given data, you must always convert them into SI units. Point 3, pressure is 2 bar. Now this bar need to be converted into Newton per meter square. We know that 1 bar equals 0.1 Newton per meter square. We have this as 0.2 Newton per meter square. While writing down the given data itself, you need to convert them into SI units. Now the temperature also need to be converted to Kelvin. Since he has given 77 degrees centigrade, which gives us 77 plus 273. Degree Kelvin. And then if final pressure becomes 7 bar, which is equal to 0.7 into 10 to the power of 6 Newton per meter square. The units are very important while doing the problem. Determine the temperature at the end of the process, the mass of the gas, the change in internal energy, and the change in enthalpy. And we have got the standard values given as R equals 287 kilojoules per kg, CV equals 0.712 kilojoules per kg, Cp equals 1.005 kilojoules per kg. You need to also observe the units of these constants. Sometimes these units are also, the values of these constants are also given different units. So you need to convert them into the standard SI units before starting to do the problem. Now let us go to one by one questions. The very first question he is asking us is to find the temperature. Since we know V1, P1, T1, and since we know P2 as well as V2, so using standard gas equation of P1 V1 by T1 is equal to P2 V2 by T2, and substituting the values of P1 V1 T1, we get the value of the temperature at the end of the process. But remember, the units have to be in SI units. That means the P1 need to be in 0.2 into 10 to the power of 6. Sorry. To the power of 6 into V1 should be in meter cube, 0.3 divided by T1 is given to us as 350 degree Kelvin equals P2 given to us as 0.7 into 10 to the power of 6 Newton per meter square, and the value of V2 remains constant and the value of T2 we need to find out. So if you simplify this, you get the value of T2 as equal to 1225 degree Kelvin. Again, while giving the answers, you need to give it back in the units which are given in the question, which means 1225 minus 273 equals 952 degree centigrade. Now again to calculate, now this is calculated, now again to calculate the mass of the gas. Since we know the values of V1, P1, T1 and also the standard value of R, we can use the standard gas equation of P1 V1 equals mR T1. Mind you, the units you need to take care, which means in case of P1 we put 0.2 into 10 to the power of 6, should be in newtons, the volume should be in meter cube, 0.3 equals m is what we have to find out, and the value of R again should be in SI units, which means 287 into T1 should be in Kelvin, which is 350 degree Kelvin. Now in order to find this value, leave these two values under this, which gives us 0.2 divided by 287 into 350. So this gives us the value of m as 0.597 kg. Find the values of T2 and m. If you go to the values of, if you go to find the value of change in internal energy, we have the formula of internal energy as mCV into T2 minus T1. We know the value of m as 0.597 kg, which we just found out, and the value of CV being constant is given as 0.712 times the temperature at the end of the process, which we calculated as 952 degrees this is again degree centigrade, so this needs to get converted into the Kelvin. 0.1225 minus the temperature at the start of the process, which is 350 degree Kelvin. Even though we put these values in degree centigrade, the answer doesn't matter, but it is required for you to get habituated to calculate using the units in Kelvin so that you don't miss anywhere. Now if you simplify this, you get the value of the change in internal energy as 372 kilojoules. Over here we'll take up another problem in constant pressure process. A quantity of gas has a volume of 0.14 meter cube, pressure 1.5 bar and temperature 100 degrees centigrade. If the gas is compressed, you need to note this point, at constant pressure, the process also is very important, until the volume becomes 0.112 meter cube. Determine the values of temperature at the end of combustion, work done, change in internal energy and heat given by gas. So for all the problems of thermodynamics, it is a must and very important to draw the PV diagram and plot the values. Since this is a constant pressure process, the curve comes horizontal to the volume axis, and since this is a combustion process, the volume at the beginning is much bigger than the volume at the end, therefore this becomes 0.1 and this becomes 0.2. Now if we plot the values, the initial volume is 0.14 meter cube and the temperature is 100 degrees centigrade and the pressure is 0.14 is 1.5 bar, and the final value is given as until the volume becomes 0.112 meter cube, the pressure remains constant, which is 1.5, temperature is what is asking us. So if we take down the given data, the data must be always converted into SI units. If you take the given data, the initial values are V1 equals 0.14 meter cube and the pressure P1 is 1.5 bar. You make sure that immediately you convert it into Newton per meter square. You must remember that 1 bar equals 0.1 Newton per meter square, and then temperature, which is 100 degrees centigrade, that should get converted to Kelvin immediately while taking down the data, and the values of P2 remain same as 0.15 in 10 to the power of 6, and the temperature is what is asking us. So if we have to find the value of temperature, we use the standard PVT relationship and substitute the values to get the value of temperature. Therefore the value of P1 becomes 0.15 into 10 to the power of 6 into V1 is 0.14 by T1 is 373 equals P2 same, and the volume of V2 is, the volume is compressed to 0.112 and the temperature is what we have to find out. Since these two will no longer be there, the value of T2 equals 0.112 into 373 by 0.14, the value of which is 298.4. Again, while you are giving values in the answer, you must convert it back into the centigrade, which means 298.4 minus 273 gives 25.4 degrees centigrade. Next question of calculating the work done. The formula for work done in a constant pressure process is P into V1 minus V2. So the value of P is 0.15 into 10 to the power of 6, and V1 is 0.14 minus V2 is 0.112. Simplifying this, you get the value of work done as 4,200 joules. We go to the next question of finding out the change in internal energy. We have the standard formula of mCV into T2 minus T1. Since we have the values of temperatures at the start and at the end of the compression, and also we have the value of CV, we need to find out the value of M. In order to find the value of M, we use general gas equation of P1V1 equals mRT1, and we substitute the values of P1 as 0.15 into 10 to the power of 6, and the value of V1 as 0.14 equals M is what we have to find out, and the value of R is given as 285, which is constant, and the temperature is 373 degree Kelvin. So from here we get the value of M as 0.15 into 10 to the power of 6 times 0.14 by 285 into 373. Simplifying this, you get the value of M as 0.197 kg. Substituting this value here, substituting the value of 0.197 here, you get the value of a change in internal energy as 0.197 into CV is 0.712 times the value of T2 minus T1 is 373. This should be T1 minus T2 since the heat is rejected. 373 minus the final temperature is less than the initial temperature. Therefore, it becomes 273 plus 25.4 becomes 298.4. So simplifying this, you get the change in internal energy as equal to 10.46 kilojoules. The units are very important in thermodynamic process. Now to find the heat given out by the gas, we have the formula of mCp into T2 minus T1 in constant temperature process. The value of M, we got it as 0.197 kg, and the value of Cp is given as 1.005 times T2 minus T1 is 373 minus, sorry, this is again T1 minus T2 minus 298.4. You get the value of heat rejected by the gas is 14.77 kilojoules per kg.